All right, we're going to work out a problem from our acid-base module. This is what is the pH of a 0.31 molarity solution of methyl ammonium iodide. Report your answer to 2 decimal places. This is where we start going down the flow chart, where we ask ourselves, is this an acid? Is this a base? Is this a salt? Is this two things? And that is essentially our complete flow chart. Methyl ammonium iodide is what we have to identify. And a big clue that it's an acid is if its name is blah blah acid, which it's not. The bases you should be getting familiar with the format of those names. And something in this might look a little familiar with a base, and you might think, that's a base, but it's not. It's a salt, and you can tell that it's a salt because it has two names. Something with two names is an ionic compound from Gen Chem 1, which is made up of a cation and an anion, which is an ionic compound is another name for salt. A salt is an ionic compound. So this is an ionic compound. So we have a salt. So what do we do when we have a salt? When we have a salt, we break it up into the ions. And so we have the methyl ammonium ion and the iodide ion. Now the iodide ion you should be familiar with. You should know what that is almost immediately. That's the I- ion. The methyl ammonium ion might be a little bit more difficult to identify, but again, I hope you're getting used to this, the way that this works in this module. The methyl ammonium ion is the cation. It's the conjugate of the methylamine, which is a base. The methyl ammonium ion is what is formed when methylamine acts like a base. The blah blah amines are the bases. They're like ammonia. And they become the blah blah ammonium ions, like ammonia becomes ammonium ion when they accept a proton, which is exactly what weak base, what bases in general do. So this is the conjugate of methylamine, and methylamine is a weak base. And therefore the conjugate is a weak acid. So the methyl ammonium ion is acidic. And that's what we have to do for the ions. Each ion we identify as it is acidic, basic, or neutral. Now so we've identified that the methyl ammonium ion is acidic. It's a weak acid. The iodide ion, again, I hope you're getting familiar with this. This is the conjugate of what? It is the conjugate of HI, hydrogen iodide, or hydroiodic acid. Hydroiodic acid is a strong acid. You must have those memorized or on a list where you can look at them quickly. And so since hydroiodic acid is a strong acid, his conjugate is neutral, and we can ignore it. The conjugate of a strong acid or a strong base is neutral, and you can ignore it. So once all is said and done, our methyl ammonium ion is going to break apart into the ions in an aqueous solution. It's going to produce the methyl ammonium ion and the iodide ion. And the iodide ion is neutral. We can ignore it. The methyl ammonium ion is a weak acid. It acts like a weak acid, and that's what's going to determine the pH. So once we've decided we have an acidic ion, we work it like a weak acid. So how do we work a weak acid? We write the equilibrium reaction. I'm going to write the generic one. I absolutely 100% could have written the formula for methyl ammonium ion, but I don't have to unless the problem specifically wants the reaction. I can write the generic weak acid where the HA is standing for, that is representing the methyl ammonium ion. All right. And what is my concentration? If you're following along on your problem set, you're probably going to have a different concentration. It is 0.31 molarity for that methyl ammonium ion. 0 and 0 minus x plus x plus x. And I need the Ka for the methyl ammonium ion. All right, this is where I would go to my Ka table to look up his Ka, but I'm not going to find this guy. I don't find ions on the Ka table. But again, earlier we said he is the conjugate of methylamine, which is a weak base, so I can find the Kb for methylamine. And what I know from my previous module is that the Ka for methylammonium ion times the Kb for methylamine, which are two conjugates, a conjugate pair, is equal to 1 times 10 to the minus 14. So I'll be able to calculate the Ka for the methylammonium ion by looking up the Kb for methylamine. So the Ka is equal to 1 times 10 to the minus 14 divided by that Kb for methylamine. So let me go look him up. Let me pull up my Kb table. And so I'll scroll down to methylamine, and his Kb is 4.4 times 10 to the minus 4. And that's going to be equal to, and this is where I go to my ICE table, it's the K for that equilibrium reaction, which is x squared all over 0.31 minus x. This is the time when I would probably go to an algebra solver. I would go to an algebra solver and I could just plug it in directly, or I can use the approximation and plug it into my calculator, or I can do it by hand, but I don't know why you would ever do it by hand. I'm going to use the approximation because this is going to work out pretty good. But again, if I wasn't sure, or if I just wanted to, I could go ahead and plug into an algebra solver. So I've got my calculator. You can't see it, it's off screen. So 1 times 10 to the minus 14 divided by 4.4 times 10 to the minus 4. I can get an intermediate value here. This is the algebra that it takes to do this, but if I get an intermediate value, don't round. Keep all the digits. I'm just going to go ahead and then multiply by 0.31 and then take the square root. And I get that x is equal to 2.65 ... times 10 to the minus 6th. And you guys can double check me. In fact, let me do it real quick because I'd hate to divide it by. Yep, all right, that's what you get. And when you get that, all right, that is the value of x. You go back up to your ICE table and say, okay, well, x was the H plus concentration. So in order to find the pH, I take the negative log of that. And I want to go to 2 decimal places. When I report it, I want to round, and so I'm going to report 5.58 for my pH of that solution.